Okay, so I suppose I'll start. Uh, I welcome you to this live session on problem solving for the course Experimental Stress Analysis, the contents of week 9. I apologize, this session should have been held on Monday, but uh, due to my poor health, I couldn't conduct it on Monday, so I asked them to postpone it today. I hope that is fine. But going forward, the rest of the sessions will be conducted on Monday. I hope to catch up with the schedule properly. Okay, so let us start with the first question today. The best practice to follow for drying the brittle coating in the brittle coating technique before conducting the experiment is to do which of the following? Is to hold coating at a lower temperature for drying and then slowly raise the temperature to the test temperature, or whether keep the coated specimen in an ice bath and reheat it, or heat the coating to an elevated temperature for drying and then slowly cool it to the test temperature. Not heat, I meant hold the coating at an elevated temperature. And D is hold the coating in front of a fan and then slowly rise the temperature to the test temperature. So it is actually recommended that because once it dries off, if we were to increase the temperature, due to temperature increase also, there is a chance that our coating might crack, which will not be representative of the stress phenomena that we are trying to study because we are in the course stress analysis. So essentially, we want our response to be based only on applied stresses and not on miscellaneous factors like temperature, unless our problem is trying to study stresses. So it is advisable that we hold the coating at an elevated temperature for drying and then slowly cool it to the test temperature at which we want to conduct the experiment. So I hope that that is clear. So if there are any questions, please feel free to ask midway while I'll move on to the next question. In this figure, the gauge length of the strain gauge is indicated by which of the following? So we have 1, 2, 3, and 4 marked by no Roman numerals here. So essentially what we have to see here is that our strain gauge, if we were to zoom in, or rather have an inner view of this, what we will be seeing is essentially grids like this, grids of wires, and which are joined here, so joined at the ends. So it is essentially the same wire that has been bent into this shape. Why this has been done is because we have having some sensitivity to applied strains, we need a longer length. But if we were to have a longer length, if we have length of about say 100 mm, if our requirement of length is 100 mm for the strain that we are anticipating to measure, then we cannot essentially claim that we are measuring strain at a point, because 100 mm is much farther from an abstract point, so to speak. So essentially what they do in the manufacturing industry is that they bend it like this into a compact. If let us say this were to be 0.3 mm or 3 mm in general, whatever that is, gauge length come in various measures as we will see later, but typically let us say if it is 3 mm and we have a number of loops, so our length of the total wire comes out to be 3n, in which case we are able to achieve the length as well as having a point phenomena, at least closer to that as compared to 100 mm length. Achieve a point measurement as well as have satisfy length requirements. So that is why we essentially have these grids. In this, it is shown in the lecture also that these edges would be made bulbous. They are much more thicker than the actual specimen. That is because our resistance is our specific resistivity L by A. So if we were to increase A, so if A increases, our resistance contribution decreases. So we don't want transverse strains to affect the resistance. We only want the longitudinal strains. So that is why the ends are made much more thicker, in which case only strain along this direction. Only strain along this direction contributes to this R, or rather change in R, which is why we have that. So essentially a strain gauge only measures the component of strain that is along this direction. So our gauge length will come out to be 1. This is the gauge length, and this is excluding of the soldering tabs, as you are clearly able to see, which is just provided to complete the circuit, and that does not uh, have a role to play essentially here. So I hope that that is clear. If you were to have any questions, please do ask midway while I continue to the next question. So I would rather erase this one because it has to end on the same side. So this goes to the soldering tabs. So I hope that that is clear. 10th required. Okay. So this question says, choose the correct statement or statements. There could be multiple answers about the brittle coating technique. So essentially, which of these pertain and hold in the brittle coating technique? Brittle coating is a whole field stress analysis technique. It can be used for qualitative assessment of stresses developed. The behavior of the coating is independent of the temperature variation. Accuracy of the accuracy of the technique achievable for most of the time is 20%, and brittle coating is sensitive to the duration of load applied. So essentially, if we see, just to give a small recap into what brittle coating is, if we were to have, let us say, some area, some domain over which I apply a coating. Over this, I apply the coating following the recommendations that are given. So what would happen is, as the name suggests, let us say that this is subjected to some kind of a load, generic load. So in which case, let us subject it to hydrostatic tension. So what would happen is, since this is brittle, we would be seeing random patterns, which are essentially cracks that have been developed. So these are cracks developed due to loading. So one main assumption or the pretense that we start with is that strain in the specimen is faithfully delivered to strain in the coating. Under this assumption, and how we hold this assumption in place is by ensuring that we follow all the recommendations that have been given by the manufacturer towards pasting the coating, towards applying the coating. Once we apply this with the assumption that the strains are faithfully satisfied, we will be able to identify cracks. As we increase the load, we will be able to see cracks develop. And essentially, we know that a brittle material fails by maximum principal stress. So what that implies is if I have a, let us say, a crack like that. So if this is the crack path, so at each and every point, a normal drawn to the crack path is what is telling me my major principal stress direction, maximum principal stress direction. So this essentially helps us in identifying what the principal stress direction is. Quantitative analysis is also possible by brittle coatings, but it has quite a lot of assumptions and it is quite cumbersome. So, as it is recommended in the lectures also, that brittle coating can be first help identify the principal stress directions. And as we know that a strain for characterizing the stress at any point, we need six stress components, six stresses we need at that point. So what we can do is at least we would be required to have three uh, strain gauges in order to measure these. Or rather, if I were to say, let me say that I'm talking in plane. In plane, I need at least three stresses. That is, let us say, along x and y and tau xy. If I have this, I can find out the stress along any other direction by stress transformation. So in order to measure these three stresses, essentially I need at least three strain gauges. But if I were to identify what the principal stress directions are, then I can reduce one station, one channel, and I can have only two strain gauges. Two strain gauges. Because along the principal stress direction and across it, we have no shear strain. So this is the brief theory behind the brittle coating technique. So is it whole field? Yes, this is whole field. It gives us information throughout the field. It is not point by point essentially, unlike a strain gauge, which is point by point. Excuse me, 1 minute. Yeah, brittle coating technique can be used for quantitative assessment of stresses. Qualitative assessment of stresses, yes, as we just discussed, uh, the crack path, the perpendicular to the crack path along the throughout the plane represents the principal stress direction. Behavior of the coating is independent of the temperature variation. This is essentially not true. Even in the lecture, it is discussed in detail that essentially even a 1 degree variation causes about plus or minus 60 microstrains difference. So this is definitely not independent of thermal variation, which needs to be accounted for, which is why essentially what we will be doing is once we take the specimen, so to circumvent this, we will do the calibration specimen. Whatever we do to the test specimen, we will also do to the calibration specimen, test specimen, so that we know what is the input that has gone into the problem, and then intelligently cull out only the information that has been caused by the physics of the problem rather than other sources of errors which can throw our results off. So brittle coating technique is not independent. It is very much behavior is very much dependent. Accuracy of the technique achievable for the most cases is plus or minus 20% of the stresses. Yes, this is true, which is why it is recommended that brittle coating be used to identify the direction of the stresses. Once we do that, essentially we reduce one station. We can use just two strain gauges at those points. This can also help us identify the stress concentration regions. In addition to the direction of principal stresses, let us say that we were to have the same thing. I'll just, or let me just draw it here itself. developed due to loading. So if let us say that I have the specimen in place and then I load it with some unknown combination. This is also there. And in some generic portion, the cracks start to appear as I increase my stresses. So what this would imply is that the once the brittle coating is faithfully pasted, this implies sort of a stress concentration where we will be able to see as we increase the load, there will be concentration of cracks in one region, and as we increase the load it will be emanating from that region. So this also helps us identify the highly stressed areas so that we can pitch our focus to those areas, and within that area if we were to analyze, we can identify principal stress directions and then study it using strain gauges. So that is a recommended approach for this. It is sensitive to the duration of load applied, yes, because if let us say if we apply it on metals, uh, if there were to be a change of change of loading conditions over time, that will get reflected. So it is very much sensitive to the duration of load applied. So I hope that that is clear. Okay, so I'll move on to the next question. So cantilever beam in bending is recommended for calibration purpose in which of the following? So essentially we know that we take, yeah, any, okay. So essentially we know that in case of a photoelastic transmission photoelasticity, we would generally go about using a disc under diametral compression, where we can find either the fringe order at the center, or we can find fringe order at multiple points and do a least square analysis in order to do the calibration. However, when it comes to other coating techniques, including strain gauge, such as brittle coating, photoelastic coating, what we would be doing is we will take a cantilever specimen. Let us say we fix this end and we have a load applied or a displacement applied, as our case may be, whether it is load controlled or displacement controlled, that is left to us. So if we were to do this, and we would be pasting the specimen here essentially at some distance. Let us call this n, and let us call this L total or whatever. So once we know this is known and the response is observed, so calibration is relating known response to observed response to evaluate the let us say the key parameter. So essentially, in photoelastic coating, we will be seeing that the key parameter happens to be our strain optic coefficient K. In the case of brittle coating, we might be trying to calibrate the failure stress of about of the coating. Similarly, for strain gauge also, we will place instead of a coating, we will be placing a strain gauge there and try to evaluate the gauge factor of the strain gauge. That has to be done experimentally. But nowadays we also have strain gauge suppliers who are test this and provide us with the gauge factor. So for most applications that is considered. So yes, this is used for the calibration in these three techniques, apart from the last technique where we have transmission photoelastic analysis, where we would be using disk, standard disk for calibration. Excuse me. So I hope that this is clear. So if there are any questions, please feel free to ask midway while I'll move on to the next question. Okay, so the strain sensitivity of a strain gauge material approaches 2 when which of the following happens? Okay, so first let us look at what strain gauge sensitivity is. So the resistance we know is specific resistance into L by A, resistance of a wire. So let us take log on both sides and applying the logarithm properties, I can get this. Now let us say if I were to differentiate this, then I would get dr by r is d rho by rho plus dl by l minus dA by A, where rho is specific resistance, A is area of the conductor of the wire, let us say, L is length of the wire. So essentially it is not hard for us to see that this quantity is nothing but our strain. This is our strain, change in length upon the length. Okay, if that be the case, then for area, it can be shown. Let me just work it out here. So the area of the wire is nothing but pi d squared by 4. So essentially, let me take log on both sides. So log of some constant pi by 4 plus 2 log of d. So if I differentiate this, this is a constant. Let me call that k rather. So this is dA by A is nothing but 2 d change in diameter by diameter. So we know that that can be related using the Poisson's ratio to dl by L. So if we were to substitute this here, we will be seeing that dr by r is nothing but d rho by rho plus 1 minus 1 plus 2 mu into dl by L. So far so good. Now strain sensitivity, what we are trying to see is for a particular amount of strain, what is the change in the resistance of the strain gauge that needs to be seen. So the strain sensitivity defined by S is nothing but dr by r divided by our strain dl by L. So if we were to divide that expression on the right by this, we'll get d rho by rho divided by dl by L plus 1 plus 2 mu. This is what we get. So this is our expression for sensitivity, dl by L. This is our expression for sensitivity. Now let us approach the question again. The strain sensitivity of the gauge material approaches 2. When does this approach 2? When Poisson's ratio, when the specific resistance, change in the specific resistance becomes 0. When the change in the specific resistance becomes 0, yes. And our, what would that imply? It will be 0 plus 1 plus 2 mu. When will this approach mu? When will this approach 2? I shouldn't put equal to. This will approach 2 when mu approaches 0.5. So when Poisson's ratio becomes 0.5 and change in the specific resistance becomes 0, then our strain sensitivity approaches 2. I hope that that is clear. This is the basic theory behind the strain gauge. And this anyway we will be discussing in more detail in the sessions to come, because the following sessions 10 to 12 is completely to do with strain gauges only. So I hope that this is clear. Okay. So let us look at this question now. Identify the correct statements related to a strain gauge. Which of these are correct? Gauge length is the active or strain sensitive length of the grid. Any length in the grid pattern can affect the strain value recorded. Any change in the grid pattern. Component of strain and direction perpendicular to the strain gauge is measured. Gauge length usually varies from zero point 0.2 to 100 mm. In stress concentration zones, longer gauge length is preferred. So let us look at this one by one. So gauge length is the active or strain sensitive length of the grid. This we saw that when we have that grid like this. So when we have the grid like this, we are essentially trying to, this is the gauge length, and this is what we are trying to essentially measure strain. So gauge length is very much active, very much sensitive, yes. Any change in the grid pattern can affect the strain value recorded. Yes, this is also true, because if I were to, let us say, take this, and if this were to be inclined like that, somewhat like that, then definitely I will be having only a component of the that is, the change in the resistance will be having only a component that is representative of the strain that we are trying to measure. So grid pattern definitely plays a big role. Component of the strain in the direction perpendicular to the strain gauge is measured. This is essentially not measured because we try to make it as thick as possible so that its effect is not creeping into our calculations. As we saw that R is rho L by A, so we increase A much more than this A, the cross section at those junctions, so that the change in resistance there is very less. So essentially this is not measured. Gauge length usually varies from zero point 0.2 to 100 mm. Yes, this is very much true. Zero point 0.2 is for very special applications. Very special applications, and this is not generally to be it is quite expensive, and very sophisticated instrumentation is required in order to paste and measure this. So this is not generally in practice, but under very special circumstances this might be used. 200 mm, depending on, for example, even if it is said in the lecture that concrete being heterogeneous material, that big a structure can accommodate 100 mm of strain gauge in order to make some meaningful measurements. But in general, the day-to-day strain gauge, if you see, it will have a gauge length of near about 3 mm. Okay, so in this is true. In stress concentration zones, longer gauge length is preferred. So let us look at this once. Let me copy this and rotate it. Okay. So if this be my gauge length, let us say that I have a Okay, so if I have a constant stress field, constant stress, then it doesn't matter, because essentially if I see, this is where I will be taking the reading. So essentially it doesn't matter because it is constant. So if I have a linear variation, linear, then I have some error, but that gets positive and negative gets cancelled out. Essentially what I'm measuring is the average stress there. So that is also acceptable. Whereas if I have stress concentration, so there will be a peak. So I'll have a stress concentration somewhat like this. So what would happen is, whatever I'm trying to measure here, sorry, 1 minute. So it will essentially average it out over the length. So this is what I will be measuring, whereas my peak will be somewhere else, and peak's value could be much higher than what I'm measuring. So in such circumstances, definitely stress concentration zones require lesser gauge length, so that my average value that I'm measuring is not way off from the peak value. So this is a very important aspect to keep in mind. This requires smaller gauge length. So if, let us say that we have a problem where we have applied brittle coating, we have found out where the stress concentration is based on the evolution of the cracks, and we have also identified the direction of the crack based on the crack path by analyzing the crack path as we discussed earlier. Now if we were to go there and paste a strain gauge, we should ensure that the length should be the gauge length of the strain gauge should be so selected that it captures this stress concentration. It should not be a huge length, so that it absolutely doesn't averages out and doesn't give you the response that needs to be measured at that point. So it should be smaller and not longer. So essentially this is not correct. Okay, so I hope that this is clear. Okay, so let us look at this next question. In order to determine the zones of stress concentration on a mild steel propeller shaft of a truck, a photoelastic coating test has to be conducted when the truck is loaded. So essentially, we are back to photoelastic coating. Okay. Using a displacement controlled experiment, the manufacturer conducts a calibration to determine the strain coefficient K for the recently developed coating material PSM1. So essentially we are dealing with PSM1. This is a, excuse me, this is a coating that has been developed recently, and we need to calibrate it by obtaining the strain coefficient K. So towards this calibration, as we already saw, a cantilever beam is made of mild steel with a thickness of 6 mm, width of 25 mm and length of 300 mm is used. The specimen properties are given here, and our coating properties are given here. Now what is said is, if the displacement is applied at 280 mm from the fixed end and the model is illuminated with white light with this wavelength, the fringe order obtained at the point that is 60 mm from the fixed end is as follows, is what is given. And we are supposed to answer some questions based on the based on what has been given. What are those? First is correction factor due to bending, then slope obtained from n versus the delta or y plot, the strain optic coefficient K of the material used, of the material. Okay. So how would we go about doing this? So let us say that we have our, let me just digress a little bit and derive it out. Okay, for we need K, that is our objective. So in the case of photoelastic calibration, we obtain the equations as follows. Sigma 1s minus sigma 2s is nothing but Es upon 1 plus mu s into n f strain by 2 times the thickness of the coating, because the light path is twice. So this is for an ideal case, but we need to account for the reinforcement effect that brings in. And what we generally do is we do not deal with epsilon, but we rather deal with K. So F epsilon is replaced by, since F epsilon is nothing but lambda by K. Similar to F sigma being lambda by capital C. Okay. So now for a cantilever beam, we are essentially taking a cantilever here, and this is fixed, and we have applied the coating. This distance is given to be 60 mm. In the question it is given, it is 60 mm from the fixed point. That is where the fringe orders are measured. The entire length is 300 mm. 300 mm is the total length, mind you. And at 280 mm, we have provided displacement. So if I were to draw it like that, 280 mm, I'm giving it displacement. So it by taking a micrometer, I'm able to give it desired displacement. So that is a displacement control setup. Okay. So this thickness is given to be 6 mm. This is steel. This is steel. And this is coating. Okay. This is 1.5 mm is what is given in the question. This is 1.5 mm. This is 6 mm. Okay. How can we recast this now? Now we know that for a cantilever, at that point we will have only normal stresses. Out of plane stresses will not exist essentially. So sigma 2s is essentially 0. Sigma 1s we can calculate. Let us see how needs to be calculated. Let us see how we can go about calculating that. Let me call this L load. Let me call this L measurement. That is where we have taken the measurement. And this is total L. Okay. So essentially 6 mm is nothing but height of the specimen or the depth of the specimen. 1.5 is height of the coating. And let the out of plane thickness of the specimen and coating be B. Okay. Now we know that delta at that point L is nothing but PL cube, P applied at L. Let me just call it P. PLL cube by 3E SIS, where S is for specimen, C is for coating. Okay, so I hope that that is clear. All right. So from here, let me back calculate P. What is it? 3 ESIS delta at L by L at L whole cube. Okay, so now that I have the load that was applied at the end, can I calculate the moment at this point? Let me, so the moment would be P bending moment at the measurement point will be P into LL minus LM. Okay. Similarly, stress at that point is nothing but M by Z. Stress at the measurement point due to this bending is moment by section modulus at that point. And I know that this is what is sigma 1s at that point because I have only one axial stress present. So sigma 1s can be given as M, which is P into LL minus LM by ZS. Okay, now substituting for P, I get sigma 1s is nothing but 3 this thing. Let me put it right away into this by ZS. Okay, now we know that IS by ZS is nothing but height of the specimen by 2. Why? Because ZS is nothing but I by T. This is a homogeneous specimen. In the case of homogeneous specimen, our neutral axis will be at the center. So essentially the distance of the extreme fiber from the neutral axis is nothing but that height by 2. So this is height by 2, homogeneous section. Okay. So these two we can replace. Let us replace this 3 ES delta L into LL minus LM by LL cube into HS by 2. This is what it comes to. Now we saw earlier that this is our for photoelastic coating. We have this. Replacing this for our problem, this is 0 and this is just this expression. So let me just put it there. this equal to RB ES upon 1 plus mu S into n lambda upon 2 HC into 1 by K. So far so good. Now what we want to do is back calculate our K from here. From here, if I back calculate my K, it will be, I'll just erase this. So K is nothing but capital K. Capital K is nothing but this upon this quantity, whatever was on the right. So what does that simplify to? Let us see. So 2 LL cube will go to the top. So it will be RB into ES. ES actually cancels out. This ES and this ES will cancel out. So I needn't write ES. RB is there upon 1 plus mu S is there. Then I have 2LL cube n lambda upon 3 2s are 6. 6. Then I have LL minus LM into HS HC into delta L. So this is what it is. So if I were to write it in a more simplified version, it will be RB into 2LL cube by, or rather this 2 will not come, it will cancel out, 3 LL minus LM into HC HS, and I shouldn't forget the 1 minus mu S into N by delta L. So this is our final formulation for obtaining K. Which is what is? First we have to calculate that. In the question if we see, the objective was to calculate K. First we have to find the correction factor for bending, slope obtained, and strain optic coefficient. Why these three? So if we look at the formula, first we have to calculate RB, then we have to calculate this slope. The rest of the things are known, we can directly calculate K. So RB, for the case of bending, if we see from our previous discussions also, it's a big formula. So yeah, any question, Mr. Rajamanna? Yeah, N is fringe order, no? Delta L, sorry. Delta L meaning the displacement that is measured there, that was applied. Okay, yeah, delta L. So in our question we have said no displacement which has been applied here. In the question it has been called as Y. Since I derived it from another way, I just named it delta L. So the idea is to be comfortable with all symbolism. Okay, all right. So RB is actually, in the case of bending, it is given as 1 plus EG upon 1 plus G into 4 times of 1 plus EG cube minus 3 into 1 minus EG squared whole square divided by 1 plus EG into 1 plus mu S upon 1 plus mu C. I am not writing this from memory. This is a standard expression given in the lecture, and it is not expected that one should remember all this. Just that it has been derived, one should know that this thing exists, where E is nothing but our EC by ES, and G is nothing but our HC by HS. So from our question, we have been given E. Let us see what EC is. In our question, it is given to be 2.3. ES is 200. HC is 1.5. HS is 6 mm. And of course, Poisson's ratio. HC is 0.38. HS is 1.3. So let us substitute for that. So EC we saw is nothing but 2.3 by 200, and this is 1.5 by 6, essentially 0.25. This ratio is nothing but 1.3 by 1.38. So let us calculate RB. I'll just calculate it. 2.3 by 200. I'll take it to be A. 1.5 by 6. I take it to be B. Okay. 1 plus EG upon 1 plus. So this is 0.8023, the first term. This term is 0.8023. Then something in the bracket. The bracket term will be 4 into 1 plus EG cube 1.0136 into 1.3 by 1.38. So RB comes out to be into 0.8023, comes out as 0.77. One can check the calculations. I'll just one minute. E into G. 3 upon 1.38 into 0.8023. Yeah, it comes to this. Okay. So the first part we have calculated. Excuse me. So the first part is 0.77. Correction factor due to bending. Now for the slope obtained using the for n by y. Essentially this is in our case in our derivation it is n versus delta L. So y I have just renamed to delta L. So let us calculate that. We can just take one Excel. Okay, so let me just present my, I'll just present the screen. Yeah, so I hope my screen is visible. Okay. Yeah, so n, and we have delta. Delta versus n is what we want to see. So this is 1, 2, 3, 4, 5, 6 in mm, and I have 0 0.4, 0 0.5, 0 0.6, 0 0.8, 1.1, 1.5. This is my value from for the fringe order that was measured. So I can do it analytically also. I prefer to do it using a graph instead by Excel. So this is the kind of variation I'm getting. So if I were to add a trend line here, so what this is doing is I can see that the trend line has some negative slope and negative error and some positive error. So this is the least squares fit. It has essentially equalized both, and I'm able to see this as the slope. So if I take this here, this is the equation of my trend line. So y is equal to mx plus c. So my m from here is 0.2143. So n by delta, that slope is 0.2143. Is what is to be understood here. So I'll just stop presenting now, and I'll go back to presenting my, yeah. So from our calculation, from Excel, we have got n by delta as 0.214 fringe per mm. Okay. So what is left is calculation of the strain optic coefficient K. So let us see that again. I'll delete this. Okay, so let us calculate this. This will be nothing but 0.77 as we have calculated RB into 1.3. 1 plus mu s is 1.3 into LL. What is LL in our question? LL is 280 and LM is 60. LL is 280 cubed by 3 into 280 minus 60 into HS HC into 0.214 is our slope. So our strain optic coefficient K comes out to be 0.77 by 1.3 into 280 cubed into, oh, I'm sorry, there is one more aspect missing. I hope you recorded this, that our lambda light is not accounted for. This is very important to account for. So here also I will have lambda. Yes, yes, exactly. So it is 577 into 10 power minus 6 since I'm doing it in mm. 280 cube into 577 10 power minus 6 is 0.214 divided by 1.3 into 3 1.5 into 6 into 280 minus 60. So I get my final value as 0.27. So my K comes out to be 0.27. What is the unit? Well, unit you can figure out for yourself. Yes, yeah, yeah, okay, okay. Uh, have you completed noting it down? Yeah. So just let me know once you're done noting, then I'll proceed. Okay. Then. Yeah, yeah. Uh, yeah, yes. Yeah, yeah, yeah. For that particular, for example, for sodium vapor, you have the lambda as 589. So for each and for every light, so light you buy, they will give the specification of lambda there. So the wavelength will be given. White light essentially doesn't have a particular wavelength because it is a mixture of colors. So yeah, so we generally take it to be the mean value of that. It will come somewhere around that. Yeah, yeah, yeah. From 400 nanometers to around 700 nanometers, it will be varying. It will be varying, but we take somewhat of a average kind of thing, and we take it to be 577. And this is, yeah, yes, yes. Okay, so let us say there is something called a spectral distribution. So for if you take a CFL, let us say, there are ways and means to measure which is the light that it is, it's white light, whatever it is emitting, which is the maximum this thing wavelength that is being emitted. So by getting that spectral distribution and taking a weighted average, we will be able to arrive at an equivalent wavelength for that. And this is mostly acceptable for general purposes. If we go into very specific purpose where it has to be extremely sensitive, then naturally we can go for a monochromatic light source, sodium vapor light or something. Because these things are very bulky, you cannot fit it into a reflection polariscope. So that is why they have a white light source and they take this to be the. And since we are conducting this on a calibration also, Whatever error that has to bring in, it will also to the test specimen, it will also bring to the calibration specimen. That is the idea behind. So essentially, that error gets taken care of. That is the idea behind it. Yeah, yeah, all right. Okay, so where were we? We have calculated k to be 0.27. Very well. Yeah, so this is 0.27 for that material. Okay, so let us look at the next question. A calibration test was done before using the brittle coating on the landing gear of an aircraft. Excuse me. A cantilever beam of aluminum was used for the calibration, and a threshold strain was found to be 600 microstrains. The material properties of the coating are given here, EC and mu C. So we are expected to calculate the failure stress sigma naught C of the coating. So as we saw in the case of calibration of a photoelastic coating, we will be evaluating K. For a brittle coating, we will be evaluating for a particular, let us say that we want to measure our threshold strain as some epsilon. For that epsilon, if I have this type of coating which has this thickness or this thing, then how will I, uh, what is the load, what is the stress at which it will crack? That is what we need to find out. Okay, so from our previous discussion of last week, we have some expressions. Let me just put them here. I'll rather put it here. Okay. So from our strain equivalence, we have epsilon 1c equal to epsilon 1s and epsilon 2c equal to epsilon 2s, where s is specimen, c is coating. Okay. So by applying our equations, we were able to see, and this was derived in detail in the last session, and this is available in the PDF that I have uploaded, into 1 minus mu c squared into, I'll have one expression, sigma 1s into 1 minus mu c mu s plus sigma 2s into mu c minus mu s. This is for the first one, that is the sigma 1 this thing, and for sigma 2, this gets reversed. So essentially I will be having this here and this here plus sigma. Okay, so what this gives us is, this gives coating stress in terms of specimen stress. These two equations. Okay, so we have been given that we have a calibration specimen which is made of aluminum, and threshold strain is 600 microstrain. All right. So We know that for a cantilever, sigma 2s is essentially 0. So from this expression, if I make sigma 2s to be 0, then I can do away with this. I have only this expression. Excuse me, sigma 1c is nothing but EC by 1 minus mu c the whole squared into sigma 1s by ES into 1 minus, or rather, let me not put it here. Yeah, so this is what we have. This is the general expression. Now, when we are looking at our threshold strain, we know that sigma 1s by ES is our strain in S. So, for our, if we look at our question, we have been asked what is the failure stress. So, at failure should be our threshold, which is 600 microstrain. So, sigma C naught is the expression for that failure stress, is nothing but, or rather, let me write it this way. Sigma 1 in the coating would be equal to sigma naught, that is the failure stress in the coating, which will be EC into 1 minus mu C mu S upon 1 minus mu C squared into epsilon this thing. Now for our case, mu S is nothing but mu A, aluminium. Let me write Al, and ES, there is no ES, so I'll skip it. So what is sigma naught C come out to be? EC we are given as 1.45, excuse me, yeah, 1.45 GPa, 1.45 E3, 1 minus mu C into mu S upon 1 minus mu C squared into 600 microstrain. So what does this come out to be? Three into 600 E minus 6 divided by 1 minus 0.42 squared. So this will come out to be this comes out to be 0.91 MPa. Okay, so far so good. So we have got this as if the material of the landing gear was aluminium, the specimen stress sigma naught S to cause this coating to crack will be what? Now again we have our general expression of sigma 1 and sigma S here. We have this expression here. So what we have been asked is, if that is made of aluminium, then how would it change? While we have sigma naught c. So essentially, it'll, since our cantilever is also made of aluminium, it will be nothing but our sigma 1 s for a given threshold strain. Since the landing gear and calibration cantilever are both aluminium, or rather, let me not go around with this. Let me work it out and derive a general expression in that case. So now when I have sigma 1 c equal to sigma naught c, that is failure stress. So what we are trying to ask is, what will this be? What should be the specimen stress such that the brittle coating breaks? So sigma 1 s is nothing but Es into 1 minus mu c squared upon Ec into 1 minus mu c mu s into sigma naught c. I have just multiplied the other side and I've got this expression. Okay, so let us do it this way now. Now I know that my coating stress sigma naught c is nothing but my uh, 0.91 MPa, since mu s is equal to mu a L. So what essentially, if I were to expand this out, in terms of this formulation, with keeping in mind that sigma s is mu s, then what I would get is essentially sigma 1s is equal to 1 minus mu s mu c mu s upon 1 minus, or rather calibration, 1 minus mu c mu s, the specimen. Here we are dealing with three Poisson's ratios. In the case of brittle coating, we have Poisson's ratio of the specimen used for calibration. Then we have Poisson's ratio of the coating. Then we have Poisson's ratio of the actual specimen that we intend to study, which is the landing gear in this case, into Es into epsilon d, or epsilon th. This is my threshold strain. Threshold strain at which I require to study. That is the strain at which my brittle coating I have calibrated to break at 0.91 MPa. Which, yeah, yeah, epsilon d. Yes, exactly. Keeping, yes, yeah. But essentially, it is problem dependent, so you can take it based on the problem. Yeah, that is the idea is that at this threshold strain, my brittle coating should crack. So I back calculate sigma naught c based on that. That's all. Now when my mu s cal is equal to mu s, then essentially I can see that this entire thing goes to 1. So my specimen stress in that case is nothing but my ES epsilon this thing, which is nothing but ES is, I'm given it is aluminium 70 into 600 microstrain to 10 power minus 6. So my specimen stress is 742. This implies that and the brittle coating would crack. Okay, now let us look at the other questions. So this will be 42 MPa. If the specimen stresses at a point where the brittle coating was applied were found to be this, the coating stress sigma 1c corresponding to the specimen stress is what? So sigma 1s is equal to 350 MPa. Sigma 2s is minus 200 MPa. In such a case, what is the coating stress is what is asked. Now we know a relationship which relates coating stress in terms of specimen stress, which are these two. Coating stress sigma 1c, sigma 2c. So these two expressions we have. Let us take it here. And put them here. Okay. So what they have asked is, what is sigma 1c? And following question also asks sigma 2c. So this is asking sigma 1c. Then for the same configuration, sigma 2c is asked. So let us calculate those first. I will move this here. Sigma 1c for EC is given to be 1.45 GPa. Mu C is given to be 0.42. ES is 70 GPa. Mu S is 0.33. So it is just a matter of substitution. This aside, this is a given data. So in such a case, sigma 1c will be EC by 70 into 1 minus 0.42 squared into 300, 1 minus 0.42 into 0.33 minus 200 into 0.42 minus 0.33. So sigma 1c comes out to be 1.45 by 70 divided by 1 minus 0.42 square. 25 by 994 into whatever comes in the bracket, which is 200 into 0.42 minus 0.33. So this comes out to be 6.047, or rather 6.05 MPa. Okay, so this is 6.05 MPa. Oh, this is 350, not 300. Let me just revise that then. In my calculation, I have taken it to be 300. This is 350 MPa. So I'll just work it out quickly. 200 into 0.42 minus 0.33. 7.13. So this is 7.13 MPa. So far so good. So this also we need to calculate. Excuse me. So I'll just take this, put it here, and I'll just change the order. Plus. So essentially sigma 2c. This will be sigma 2c. So it is again the same 25 by 994 into some quantity. 350 into 0.42 minus 0.33 into minus 7039 by 50 comes out as minus 3.54. So this is minus 3.54. Okay, 7.13 and 3.54. So we have got sigma 1c as now the question asks, if the cantilever was made of mild steel instead of aluminium, what would be the specimen stress considering the threshold strain? Is what is asked. So instead of aluminium, what would have been the specimen stress corresponding to was used. So we saw here that essentially our specimen stress is given as this. So if I take it here, so yeah, if the cantilever is made of mild steel, where E of steel is 210 and mu of steel is 0.26, then what should be the specimen stress corresponding to the threshold strain is what is asked. So essentially mu s cal is 0.26 and mu s remains 0.33, which is aluminium, since the landing gear is aluminium. So that is what we need to account for. Why don't we do that here itself? Right. So this is nothing but 1 minus 0.42 into 0.26 divided by 1 minus 0.42 into 0.33 into ES mu s. The specimen and this thing remains the same, E3 into 600 microstrain. This is what my sigma 1 s would have to be. So what does this come out to be? Instead of 42 MPa, which we got, it will be 42 into this quantity, which was earlier 1. That will no longer be 1. So it will just get corrected by some factor. What is that factor? 26 divided by 1 minus 0.42 into 0.33. This 1.034 into 42, which comes out to be 43.43. So if the cantilever was made of steel, then the specimen stress would have to be 43.43 in order for our to achieve the same threshold strain. So cantilever, the material used for calibration is very essential. We see that Poisson's ratio plays a big nuisance value. And in the case of brittle coating, we have to deal with 3 Poisson's ratios. So in order to simplify this, we generally use our specimen for calibration the same as our actual specimen to be studied in the problem. So I hope that this is clear. So I needn't have this here. I'll just erase this. And that ends this question. So again, so I have run out of questions now. So I've solved everything. So in case there are any questions, you please raise them. Yeah, 1 minute. Sorry. Yeah. 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 Yeah, so is there any question here, or you're noting it down, or okay, okay, please go ahead. 12th and 13th, yeah, these two. Okay, okay. Yeah, yeah. Okay. I see. Okay, okay. Yeah, yeah. In the 13th one, it is asking sigma 2c. So over here, no? Same, exactly the same. For the same stress condition, sigma 1s and sigma 2s equal to 350 and minus 200. What is sigma 1c? What is sigma 2c? Yes, sigma 2c. Yeah, yeah. First, meaning the first question. Yeah, sure. But you are getting this PDF, aren't you? Okay. Right, right, right. All right, all right, all right. Okay. Yeah, actually, two more. This coming Monday, I'll be conducting week 10, and then following, I'll go till week 12. Yeah, yeah. No, that is too much to cover in one session. But I have already uploaded the video. So, if you have any questions based on that, those you can just raise it there. Yeah, because each session we are holding it for 2 hours, right? So the entire assignments have been solved. So the if the total course assignment needs to be solved, it will take much more time, which has already been done in the videos, and those I have uploaded. So based on after going through those videos and questions, if there are any doubts, I'm absolutely open to answering them in that session. Yeah, yeah, yeah. Okay, so other than that, today I've run out of questions. So anyway, more on strain gauges will be conducted this coming Monday for week 10. So other than that, if you have no questions, you can consider leaving. Okay, yeah, yeah. Thank you. Right, right. Okay, thank you very much for the comments. And okay, I'll see you on Monday then. Thank you. Yeah, yeah, yeah. Bye.